Good morning again, nerds, and welcome to the exciting conclusion of Section 2.2. The moment you've all been waiting for. Using mathematics to model the real world. Word problems, that's right. We're going to be talking about real-world uses of quadratics now. And we start that with the most real-world use of quadratic, and that is balls in the air. Actually, technically anything in the air. Falling from the sky, I should say. Vertical free fall motion. Okay? This isn't a physics class, so I'm not going to tell you have to have these equations memorized. If I need you to use them, I will give them to you. But you do need to understand what they do and how to use them. The height, lowercase s, and vertical velocity, v, of an object in free fall are given by these equations. Now, these equations assume that you're in a vacuum, meaning there is no air resistance. Okay? It also assumes that we're on Earth, where gravity is a constant and a known constant value. And by the way, we use lowercase s for position. We talked about this. We talked about position with, was it the last lesson? Yeah, when I talked about speeds, velocities, accelerations, things like that. And I said changing position over time is velocity. Well, lowercase s is the variable that mathematicians or physicists, one of the two, I'm not sure, decided to use for your positions. So we're using it for height because it's literally the height, the position above ground. Okay. Anyway. G is going to stand for the gravity constant, and if we're using American units, then we're talking feet per second, feet per second squared. I know it's supposed to be 16, but that's because this equation has a negative 1/2, and negative 1/2 of 32 is negative 16. So if you were in physics and you're wondering why it says 32, that's why. And if you're using what the rest of the world uses, except for 3 countries, one of them being us, meters per second squared. Cool beans? Cool beans? Okay, great. So 9.8 meters per second squared. But again, these two numbers are assuming that we have absolutely no air to contend with. No friction from air. T is time. V sub 0 means initial velocity, meaning what the velocity was when we started. And S sub 0 is initial position, in this case, initial height. Cool with that? Our vertical velocity, you already know what T is, you already know what G is. We already talked about V sub 0 being initial velocity. So this is going to give us our height over time and our vertical velocity over time. Cool? Cool. Students conduct an experiment to model gravity and free fall motion. They did this by tossing a ball directly above a detection device. The ball went up, then fell directly back down onto the detection device. The time and height data are recorded in this table right here. We're going to use this data to write models for the height and the vertical velocity of the ball. So we're not going to start plugging things into these equations right now. No, we're going to let our calculators do that for us. Because again, these assume that there's no air, that it's perfect conditions. And well, if this was students with a detection device, we're all going to assume that they were not out in space and that they were on this planet and there was air. So instead, we're going to let our calculator figure out some stuff for us. So we're going to use this to model height and initial velocity of our ball. We don't need to read any further for now, other than store the model, which I'll show you on the calculator. This is a quadratic. So we will input this data, and then we will do quadratic regression with it instead of linear regression. Grab a calculator. Oh no! If I break it, I gotta buy another one. Grab your calculator and go to Stat Edit so that you can fill out your new lists. Stat Edit. You'll notice my lists are blank. If your lists are not blank, I'm just reminding you, go up to the L1, hit clear, and then enter, and it will clear the list for you. Same thing for L2, and if you have anything in L3, same thing for L3. Take your time. Input these values. Your times are your L1s. Be very careful. Put them in accurately. And the heights are your L2. Be very careful. Put them in accurately. Because if a single digit is wrong, your answer won't match mine. You don't have to put in the zeros at the end of the decimals. I'm also not going to use the 0 on the front. I'm just typing point. And don't worry, when you type these in, sometimes it'll round the decimals for you. Don't worry about that. It knows what you typed, it just couldn't display it. I'm going to pause the video while I put this data in. They don't need to watch this. There. My data's in. I took the time to recheck it too, just to make sure that I didn't make any mistakes typing it. It's very easy to fat finger the keys and make a mistake. So am I going to make you be able to do this kind of stuff on your next assessment with your graphing calculator? Yes, I am. You need to be able to do this on your graphing calculators. Yes, sir? That's what I was saying. Because it can only show you 4 decimals, it will round. However, it knows what you typed. So, I mean, at least it should. Yeah, see, if I scroll up to the 0.8317, it shows me the value had a 3 on the end of it, but it just rounds to fit it on the screen. But don't worry, you don't round, you type exactly what you needed it to be. Are we ready to do some regression? Okay. No, not yet. 2 more things. So even though I paused it, we still gotta wait. This is quality content on YouTube, let me tell you. Quality. Okay, she's there. Stat. Go over to Calc. And instead of scrolling down to linreg, we're going to go down to the 5th one, quadreg. We are doing quadratic regression. So it's in the same place as linear regression. Hit enter. Don't go all the way down to calculate, because we are going to do stuff with this model. We're going to have the calculator do it for us. You should have your x list as L1, your y list as L2. Come down to store regression equation, because we need to store it into our calculator, because we want this calculator to graph our model for us and do other stuff. Here's how we store an equation. Vars right here below your arrow keys. We want it to be able to graph it, which is y equals, so we have to go over to y vars. And our calculators are currently in function mode because, y equals, so hit enter on function. And I'm just going to hit enter on y1. Now what that will do is, it'll tell this calculator, whatever regression model you come up with, put that into my y equals menu as my y1. That's what that tells me. Scroll down and hit calculate. It's going to flash a little bit and boom, there it is. Do you remember when we talked about correlation coefficient and coefficient of determination? Do you guys remember that? R and R squared? Look at this R squared. 0.999. It's almost perfect. What stops it from being perfect? Air. That's what got in the way. If we had performed this experiment in a vacuum, it would have been a perfect R squared equals 1. Because, in a vacuum, gravity will follow exactly what we think it should. But when you're not in a vacuum, wind gets in the way. Okay. So we have our model. We don't need to even write this down. But I do want to take note of something. And because I'm taking note of something, it's the only reason why I am going to write it. Now I'm going to round to 3 decimals because, what if the AP exam said, what is the equation? Or what if my test said, what is the equation? So we're going to round to 3 decimals. My model for height over time is negative 4.677 t squared plus 3, come on now, don't go dark on me now, 3.758 t plus 1.045. There. So that's our model to 3 decimals. And we're going to recall in a minute that R squared was 0.999, almost perfect. Almost perfect. That says that over 99.9% of the variability in the y's can be attributed to the change in x. It's almost perfect. Yes? This screen, you mean?
No, we have the screen.
Okay.
Yeah, we have different numbers.
I got the same numbers as you. Because guess what?
You double checked your digits?
Oh.
Okay. He says he double checked his digits. I'm going to pause it and let you come up. Let me see your list. Now that I proved Mark remarkably wrong, because he's the one that made the mistake, and definitely wasn't me making a mistake and forgetting a digit in my list. Definitely never would have happened to me. We have a new regression here. So is it negative 4.676? There we go. 3.758. That's the same. 1.045. That's the same. Okay, so it threw this off by 1,000th. Yikes. Would it have been wrong on the AP exam? I don't know.
So is that supposed to be a 6 or 7?
It should have been a 6.
I have a 6.
Okay, I didn't. I had a 7.
Oh.
Okay, anyway. Yes? Jesus. All right. Pause. Okay, eventually we're going to finish this lesson. Anyway, there is our model. And 2 things about this model. 1, it shows us our initial velocity. So I'm going to write that right here, because that's from up here, if you look. The b value is your initial velocity. And 2, after some math, it shows us what it thinks is gravity. Well, it shows us negative 1/2 of gravity. So we're going to need to solve for our gravity. And once we have that, we'll take gravity and this initial velocity, and we can fill out this equation here to get our velocity over time equation. Okay, so we said, the calculator says that negative 1/2 of gravity is negative 4.676. So to figure out what our calculators think gravity is, we will multiply both sides by negative 2. Negative 4.676 times negative 2 is about 9.352. And it makes sense. We're doing meters. 9.352. So did it get exactly the 9.8? No, it didn't. But again, wind resistance, air resistance is what caused gravity to be slightly off in our question. We can now write our initial velocity equation. Or not initial, but our vertical velocity equation. It is negative gravity, so negative 9.352 t, plus initial velocity. Great. There we are. I put the g value right here with a negative sign in front of it and initial velocity, which is right there at the end. Okay? So we found our 2 models, and we stored it as y equals. We are ready to rock and roll. Use these models to predict the maximum height and the vertical velocity when it hits the face of the collection device. Okay, this is a negative quadratic. Where are we going to find its maximum height? Not what's the answer, but because it's a quadratic, where will we find it? At its vertex. Good. Go to y equals. Yes, it's there for us because we told it to be there. So just graph zoom 6. And there it is. Our window is way too large. First of all, this isn't Back to the Future, so there's no time travel. Our x minimum on our window should be 0. Our x maximum should only go a little bit past x equals 1. Look at our y values. They don't go above 2. And since this ball is not going to blast right through the collection device and then go through the table, yes?
My vertex is like really fat.
Yeah, mine is too.
Your vertex is fat? What does that mean?
The line is so fat.
It's like chunky.
Oh gosh. More than likely you have a stat plot still turned on.
Oh, I don't know.
There you go.
Thank you.
You're welcome. We're going to do that next, but first we're going to change our window. First we're going to change our window. Anyway, like I was saying, go to your window, There's no time travel, so x minimum is 0. X maximum, you could take it to 2 if you want to, but it really doesn't go past much past 1. So I'm going to take it to like 1.25. I don't know. And then have your tick marks. I don't know. Say go by 2.25s. That'll give you 5 tick marks. Whatever. The minimum height is going to be 0. However, I know what's on the back of these notes, so I want to have a small negative value for my minimum. Negative 0.1. Okay? Trust me on that one. And y maximum, it didn't even hit 2, so I'm just going to go to 2. And I'll make my y scale 0.2, whatever. Now when I hit graph, it's going to be a pretty path of the ball. Whee! Look how nice that is. Remember, we're plotting vertical height over time. So this ball isn't going sideways. It's just that when you plot heights over time, because things are being pulled down by gravity, they make quadratics. You guys said that I'm going to be able to find my maximum height at the vertex, correct? So we're going to find its maximum using second trace maximum. Second trace maximum is number 4. Got to get to the left of the maximum, so I'm just going to scroll over there. Hit enter. Go to the right of the maximum, scroll over there and hit enter. Go in between them as a nice guess. Fine, that feels like a good guess. Hit enter. And it tells you what the maximum height is and when it occurs. This maximum height ended up being about 1.8 meters at 0.402 seconds. .8 meters at 0.402 seconds. Bless you. That was the vertex of my quadratic. Second trace maximum. Go left, go right, go center, and it'll give you where and when the maximum occurs. Cool with that idea? Great. Let's talk about the next part. The next part says find the vertical velocity when it hits the collection device. I'm going to drop a pin, and hopefully it lands under the camera. And you tell me, what is the height when it hits the collection device? 0. Where is that on this picture? The x-axis. The x-intercept is a height of 0. I need to know when that occurs. I need that x value. So what do? You could do second trace 0, go left, go right, and guess. But I'm a big fan of going to y equals and just hitting y2 as 0. And then doing second trace intersect. And just because second trace intersect I feel like is really fast. So we do that. And then I'll do second trace intersect. Yes, yes, scroll. I just like second trace intersect. I just prefer it. That's a me thing. Guess happens at 1.022 seconds. Comfortable with that idea and why it's there? Because the x-axis is height of 0. And I just found out that it's going to take just over 1 second, 1.022 seconds, to have a height of 0. Now that we know when that occurs, I can figure out what my vertical velocity is there by putting that time into the velocity equation. Our velocity at 1.22022 seconds is negative 9.352 . That's going to give us our vertical velocity when this thing struck the device. And I'm just typing that on a calculator. So to 3 decimals, it actually ends up becoming negative 5.8. So 3 decimals actually rounds all the way up to a single decimal. Negative 5.8 meters per second. Remember your units. Negative 5.8 meters per second. That's not a speed, it's a velocity. The reason why it's negative is because the object was falling. On the way up, the vertical speeds, the vertical velocities would have been positive values. Okay? And I still didn't clear anything out of my calculator because the back of this paper is going to have more to do with that model. But can I flip the paper over without anybody panicking yet? Yes. Awesome. So we've talked when we were doing linear regression about how we can tell if a model is good or not. But what we did to predict whether or not a model was good was we used our R value. And we said if the R value is close to 1 or negative 1, you have a very good model. Talking about strong correlations, right? Strong positive correlation gets close to 1. Strong negative correlation gets close to negative 1. And I also told you about the coefficient of determination. Words are hard this morning. It's just R squared. So the closer R squared gets to the number 1, the better your model is. Our R squared was 0.9993. So almost perfect regression. But it wasn't perfect, was it? What that means is there's a small amount of error. So unless you get an R squared of equal to 1, whatever you just found will have a small amount of error. The difference between what our model predicted and what the actual values are is called a residual. It's kind of like a residue, a leftover. What I'm getting at is if I used time equals 0.1080 in this model, would it give me exactly this height? No. It would be off by just a little. And the difference between what the model predicts and what the actual value is called its residual. And the values of the residuals tell us whether or not we have a good model when we plot them against the x values. That means we now have, technically, 4 ways of telling if a model was a good model or not. Way number 1, the R value, the correlation coefficient. If it's close to 1 or negative 1, that's a good model. Way number 2, square it. If R squared is close to positive 1, that's a good model. Way number 3, if the model type is supported by real-world theory like gravity or product prices being linear and things like that. Those are real-world mathematics. They're going to generate good models. The last way that we can tell if a model is good or not is by creating a scatter plot of the residual values. And if the residual values are randomly spread around the x-axis and relatively close to the x-axis, that's another way of seeing if it's a good model. So a bad model would have an R value that's close to 0, which means an R squared value close to 0. If it's not supported by real-world theory, like if you found out that gravity was 0.2, we're like, well, no, it's not. Maybe this was done on the moon or something like that. See? Or, the new one, if you were to create a scatter plot with your residual values around the x-axis, and they create an obvious shape or pattern, then that's a bad model. And you'll see that happen in the notes here in a minute. Notice all this space I left you? That's because you're going to take notes on how to do this. It's going to be in the video, but you need to be able to do it. So I strongly suggest that you do this on your own calculators. Here we go. Using the model generated from the ball experiment that we just did, generate a residual list. Stat, edit. Don't clear anything. Go to L3 and scroll up to L3. We're about to give L3 a command. This is like Excel. Have you ever put an equation into Excel and then it calculates things for you? We're about to do that. We're about to assign an operation, so to speak, to the entire list. Pay attention, here it comes, guys. Second stat. Second stat brings you to this menu. And on this menu, somewhere down the line, you'll have the word resid. If it's an old operating system, you'll be able to see it right now. If it's a new operating system, it'll be at the bottom of the list. Either way, it's there somewhere. It says resid. You're going to hit enter on resid. This calculator is saying, hey, did you want L3 to be the L residuals? And you go, yes, I did, by hitting enter one more time. Boom. Yes. What's up? You cleared the list? Not deleted. You cleared. Nope. There's no way to bring it back. You know what? No, it's gone. Sorry. Nope. As far as I know, it's gone. Sorry. You'll just have to watch the video. Error data type. Oh, God. All right. Bring me the calculator. Come on. Quick. I don't want to pause the video. Quick. Error data type. Go to. You didn't go up to L3 like I said to. Clear. You have to do it here. Second stat. Resid. There you go. There. Look at how small those residual values are. I mean, the biggest one is, the biggest positive one is 0.013, and the quote-unquote biggest negative one is negative 0.014. So they're incredibly small, aren't they? So I'm going to go back to graph, and I don't have any scatter plots on, do I? Time to turn on some scatter plots. Go to y equals. And if you go up to plot 1 and hit enter, it'll bring back Charlie's dots that I erased a minute ago. And I'm going to hit graph. There's my dots. And we can see that model goes relatively through those dots. This y equals 0 line is useless now. I'm just going to get rid of it because it's not doing anything. Anyway, I need another scatter plot turned on. But if you turn on plot 2, watch what happens. Graph. What are those? Those are my residuals. They are very close to the x-axis, you mean? That's what we wanted. Yes?
Why didn't it graph the residuals? It graphed the same points.
It graphed the same points. Interesting. Did anybody else's do that without graphing the residuals? It did, right? Okay, so what happened is I have already set up the option for it to show me these residuals as a different scatter plot. Here's how you are going to make that happen. Second, stat plot. So second y equals. Go down to where it says plot 2. See how mine says L1, L3? Yours says L1, L2. You're going to hit enter right there. And you're going to scroll down to where it says Y list. And you'll do L3. Remember, L3, you'd have to hit second 3 to make it work. To get rid of the things on the bottom? No, to get the things on the bottom. Yeah, you wanted these down here. They are the residuals. So do you see how these residuals are relatively close to the x-axis, scattered above and below, and they don't form any kind of odd shape or pattern? Because of that, we know we have a good model. Cool with that? So I'm actually going to answer the question where it says analyze the residuals. I plotted them. There they are. Here's the residual analysis. You just write this wherever you have space. Because residuals are randomly scattered around x-axis with no pattern or shape, we have a good model. I mean, we already knew we had a good model because r squared was 0.9993. But did you see what it did to the... He can't read my handwriting. Because the residuals are randomly scattered around the x-axis with no pattern or shape, we have a good model. Okay. And if you really wanted to, you could zoom in to see these residuals much better. If you like went to your window and you changed your y min and y max to much smaller numbers. See? But they are randomly scattered around the x-axis with no pattern or shape. And they're very small numbers. Yes? Now, you messed up again? Okay, what? Well, hold on, I'm going to pause the video. Okay, we're going to try to finish these notes today. Let's go ahead and see what a bad model would have looked like. Let's see a bad model. What I'm going to do is I'm going to go into y equals, and I'm going to clear this equation out. So I cleared y1. Go into y equals, clear y1. Leave your stat plots on. Just leave them on. Then I'm going to go to stat edit. Bless you. I'm going to go up to L3 and hit clear enter. So I'm clearing out my residuals because I'm about to create a bad model and generate a new residual list. Alrighty? So stat, calc. We already know that this quadratic was a gorgeous model, right? Let's go ahead and say it was a straight line. Let's get a linear regression and store the linear regression as L1. Vars, y vars, function, y1. Vars, y vars, function, y1. And hit calculate. And there's our equation. Look, we already know that it's a bad model without those residuals because r squared is almost 0. So that's a bad model, okay? But I want you to see what bad residuals look like. You saw good residuals. They just kind of spread themselves around the x-axis randomly. Go stat, edit, stat edit, go back to the L3, go up to highlight L3, second stat, and put resid back on there, and hit enter. It just generated new residuals for me. Now look at those residuals. They go between negative 0.5 and 0.3. So I'm going to go to my window. And my y minimum, I'm going to make negative, what did I say? I'll just do negative 0.5 and positive 0.5. How about that? And have my y scale go by 0.1s. Look at those residuals. What shape is that? It's quadratic. So because these residuals form an obvious pattern, this is a bad model. Because those residuals basically told you should have picked a quadratic, stupid. That's basically what that says. In fact, if you make the window large enough so that you can see the original scatter plot, and let's zoom 6. Like, okay, jokes. I mean, look how bad that is. What was the original window? Do you remember? 0 to 1.25 and 0 to 2. But I'm going to go to negative 0.5 up to 2. Uh-oh, window range. What did I do wrong? Window. Oh, whoops. Y minimum is negative 0.5. Y maximum was 2.5. No, I just did 2, didn't I? Y scale 0.2. Graph, much better. I mean, look, it's such a bad model, but the red dots are the ones we're looking at. So what we say is, because the residuals formed an obvious quadratic pattern, we have a bad model. And there it be, nerds.